Okay, we have 4 sessions, which are an hour and a half, but it's a little bit difficult for you to concentrate for an hour and a half. So in the middle of each session, we'll have a very short pause. Please don't disappear, but at least just stand up and sort of walk around, and we'll open the windows for a bit to get some fresh air in and everything like that, okay? If I think at these pauses, then we can have a bit more time for proper questions, and then if you can come to the microphone, because then it gets recorded. And, you know, what we want to do with this tape is to make it available to other people. So it's very, very important if you ask questions, because then you can guarantee that whoever else is watching it, somebody will have the same questions. Okay? So in terms of organization, you should have 5 copies in front of you. In the first session here, we'll go through really the very basics, what is concrete, and then a little bit about how we make cement and why that's important. In the second session, we'll tackle the subject of hydration, and particularly from the perspective that you need, which is how does it end up like? You know, you start with cement grains and water, we end up with a hardened block, and what really is in that hardened block at a microstructural level. This afternoon, then, we'll look at how supplementary cementitious materials affect this microstructure, and finally, we'll talk about characterization methods. Okay. Now, this is the first course. The first course, I think, 6 are planned, and for the next 2 courses, things are already decided, but after that, we have a bit of flexibility. So if you think there are major areas that we don't have on the list at present, please think about that and let us know. Okay, so let's get started. So what I want to do in this first part is 2 things. First of all, give you an idea of why concrete is such an important material and why we should bother to study it. And secondly, look at the very basics of how you make concrete, particularly stressing the importance of understanding the repetition of volumes, because this is really what it's all about. So the background to this subject, as I'm going to tell you about, is that concrete is the most used material in the world. Let's see if I can swap this around. Oh dear. Right, major disaster. Just if I have it on the other side and I'm turning to the screen the whole time, it won't work. Okay, sorry, folks, time out here. Okay, it's not going to work, failed completely. Is that still working? No. Hello? Yeah. Okay, so I'm sorry, the sound's going to be, is that coming through now? Yeah, okay. Right, so back to the beginning. Why concrete is the most used material and why we need to work on improving sustainability. So this is just a very basic graph. It's a little bit old, but don't worry about that because things change in proportion. And what this graph shows is this relationship between the annual production of different materials and their cost. And this is very, very important because what it underlines is that we see concrete is by far and away the most used material in the world, and the main reason for that is because it's very cheap. Okay? So don't let's kid ourselves that it's this really miracle material. It's quite an interesting material, but the main reason it's so used is because it's very cheap. And that also limits us somewhat in what we can do to improve concrete. Because, you know, we could come along with solutions, but if those solutions made the cost increase by a huge amount, that wouldn't make any sense. Now, why is it the most used material and so cheap? Well, first of all, we can make it almost anywhere. This is, in fact, becoming increasingly important because we hear more and more about materials which are available in short supply. For example, there's a big debate about iridium, which is used in flat screens. If people go on having more and more televisions with flat screens, there simply isn't enough iridium in the world to make them all. That's not true with concrete, as we're going to come back to several times. It's made of the most abundant elements in the Earth's planet. Secondly, you make it as this grey powder, and then you can move that grey powder around very, very easily, and you get it to site, and you just add water and stir. I mean, this is just incredibly simple. It's actually a major drawback because it means the people who make concrete on site don't have to have a particular level of sophistication and may not understand the basics of what's important in concrete, which can lead to problems. But generally, concrete is quite forgiving. And you make it, you add water and stir, and then you can fill almost any form. It sets and hardens at room temperature, and there's very little overall volume change. And there's really no other material that has these properties. You think about something like steel, you've got to prefabricate the elements, and then you've got to ship them to the site on the road or whatever. You think about materials like clays or bricks, you've got to fire them in an oven, and they have a huge amount of shrinkage. So concrete is really quite unique in these properties. If it's correctly made, it will be very durable, and it keeps out water. And finally, as I've already said, it's incredibly cheap. Now, the fact it's incredibly cheap also means that, contrary to what a lot of people think, the associated energy and CO2 emissions of concrete are actually very low. Here we see a table where we compare most common materials, and on the left here I've displayed those in a relative format. These are just scaled to 100%, and you can see concrete is way down here. It actually has lower energy and CO2 emissions even than something like wood, and much, much less than things like steel and aluminium. Of course, here you can see another problem, which you can see that for both steel and aluminium, you can see the very, very big difference between recycled material and virgin material. And this is what drives the tremendous effort to collect all your drinks cans and make sure they're all recycled. But it also means that for concrete, because you have such very low energy and CO2 at the first place, even though you can recycle these materials, often it doesn't make sense energetically. Because if you have to transport concrete rubble from one site to another, you can end up expending a lot more energy than you can making new concrete. So intrinsically, it's a very low energy and low CO2 material, but because we have these enormous volumes produced, this means that cement production worldwide accounts for about 5 to 8% of man-made CO2 emissions. And this is where the pressure comes really to continue to improve this. Now, in understanding how we can go about improving this, we need to know particularly what's the origin of those CO2 emissions. So on this chart here, we see the origin of this CO2 broken down into two parts. Here on the left, we have 40%, which comes from the fuel. Now, that's the same as you get in most production processes. You have to provide heat to get the changes, to give you the material you want. This is a cement kiln. I'll talk a bit more about that after the break. It looks a kind of rather rustic kind of equipment, but in fact, with progress that's been made in the last 30 or 40 years, it's now a very efficient thermal process. It's one of the most efficient thermal processes there is. It's reckoned to be about 80% of theoretical efficiency, as opposed to something like thermal power generation, which is more like at 60% or less. Furthermore, because of the flexibility of this cement kiln, you can use actually a lot of waste fuels, and now typically in state-of-the-art plants, about 80% of the fuel you need will come from waste. And these wastes can be very varied and diverse, things like car tires, offcuts from making sofas and things like this, animal bones, just about everything can be put back into a cement plant and its calorific value used. So where we need to look is on this side, this 60% of emissions here, and this is more problematic. This 60% here comes from the dissociation of calcium carbonate. So as we'll see later, the main ingredient to make cement is limestone calcium carbonate, and the first step in the production of cement is to heat this limestone up, and it then dissociates into calcium oxide and CO2. And there are a large number of ways, as we'll see, to reduce this amount of calcium carbonate, but if we do that, it's actually going to have an impact on changing the basic chemistry of the final cement. And if we change the basic chemistry of the final cement, this is going to change the whole way it reacts and performs in service. And if we don't understand these changes, then we can't use these low CO2 materials. And this is very much the context in which this Transcend project is developed, that as we move to low CO2 materials, we need to be able to understand how to use them. Now, this sounds a big challenge because it says, okay, we're going to have all different cements. We may find in 10 or 20 years we have many hundreds of different types of cement. How can we possibly understand how they all behave? Well, again, it comes down to this basic chemistry. So if we look here on the left, what we see is the distribution of elements in the Earth's crust. And it's quite amazing that the 8 most abundant, which are oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium, that's only 8 elements. This already constitutes 98.2% of the Earth's crust. So, you know, everything else, all the other 100-odd other elements are all in this 1.6% here. So this means that we only really have the choice of using basically these 8 elements, but 8 is a number that really it's possible to actually determine more or less everything that's going to go on with those 8 elements. It's not a completely intractable task. And as I've shown here, this is the present composition of a typical cement, and you see the big difference here is the huge extra amount of calcium, and that's our target. How can we reduce the amount of calcium oxide to make cements more sustainable? Now, what's been done so far is what's called reducing the clinker factor. Okay, so we have the cement kiln. This produces this material called clinker. We grind it up, and that makes cement. Okay, and what is already being done all around the world is that when we grind the clinker up to make cement, we can add in other materials. And these shows the figures from Holcim. You would have similar figures from all the major cement producers. And you see over the last 20 years or so that gradually the amount of clinker on average in cement has been coming down and down. And this amount of reduction in clinker translates almost directly into a proportional reduction in the CO2 emissions. Now, what are we using to substitute the clinker? Well, we're using a very wide variety of things, mainly in Europe and most other industrialized countries. The main 2 materials we're using are fly ash and blast furnace slag. And what's important to notice on this slide is that these are kind of substitutes that actually work very well in cement, but the amount of them available is really quite small compared to the total amount of cement produced. And it's not likely that the supply of these materials is going to increase that much. It's very much a local thing. It varies from country to country. For example, in China, where they're building a coal-fired power station every week or so, then of course you're going to see large amounts of fly ash being available for the foreseeable future. But in terms of steel, steel makers are already looking to see if there are alternatives to blast furnaces, because they also have this pressure of sustainability. So we may find that blast furnace slag is coming in increasingly shorter supply. So where can we go? Well, you see there's a large number of materials out here which are used today in very, very small amounts. Their amounts could increase. And particularly, I think it's interesting that this material called metakaolin, or more generally calcined clays, that means clays that are heated up to about 600 to 800 degrees, this can give an active material you can use in cements, and clays are available almost everywhere in the world. Secondly, we also have a lot of natural materials which are naturally reactive. And finally, we have almost unlimited supplies of limestone. And limestone, even though it has a very limited reactivity, can also be very effectively used as a substitute for clinker. So this is what's projected to be the growth in demand for cement. This is really inevitable because it's a consequence of the increasing world population. It's projected that by 2050, the population of the world will be 9 million as opposed to 7 million today. And this explains why there's foreseen to be this tremendous growth in demand for other developing countries. You see, China is forecast to reach a peak and then decline somewhat. India keeps growing, and the industrialized countries really stay fairly constant. So to meet this demand, due to what I've already told you about the distribution of elements in the earth, etc., we have to adopt a multitude of solutions. There's no one single magic solution. It's not like, journalists often come up and said, have you got a new miracle cement? Now, you've seen the elements in the Earth's crust. You could make cements out of like barium silicate or something like that, but it would be totally nonsensical because there's nowhere near enough barium available as opposed to calcium. So we've got to use what we have, and we've got to use a wide range of solutions. Here I show one. Here several. We can look about increasing substitutions of clinker. We can think about new clinkers. We can think about higher strength concretes. We can have new substitutes. We can have alkylated activated materials, etc. And if we use a combination of these solutions, I think this is the only way we can see to keep the CO2 emissions associated with building under control. And this approach is what I call an open concrete approach. We have to be able to use a wide variety of different solutions. So that's just summarized here that there are all these solutions. The key point here is this. These new solutions can only be successful if we can provide the basis in understanding and performance tests for users to have confidence. And this goes to the heart of what this project is about. Because what users need to have confidence in is, will these materials last? It's very easy to make concrete in a lab and test the strength at 28 days and say, okay, we've got the strength we need. What's very difficult to do is to say, is this concrete going to be as good in 40, 50, 100 years as the present concretes we're using? Because we really have great difficulty compressing this aging effect of cement and studying this on a short-term basis of 2 or 3 years. And so this is why we need to understand what goes on with water, because all the degradation processes, and you're going to hear much more about this on Wednesday. Wednesday is really focusing on pore structure, different degradation reactions, but nearly all of these degradation reactions are brought about by the interaction of water with the concrete. And if we can understand that on a basic level, which is what we hope to do in this project, then we can come a long way forward in replying to this demand here. And so this has given rise to what we call the Open Concrete Roadmap. This is the overall Nanocem project. I'm not going to go into all the details here because it's very, very complicated. But this has basically got two main blocks. The first block here is the fundamentals. How do we understand what phases is there? How do we understand the structure? How do we understand the microstructure? And this block here is about how we assess performance in all sorts of different dimensions, from the rheology of how we put the concrete in place, the development of mechanical properties, through these various terms of degradation, protection of reinforcement, etc. And this overlaid on it shows where the Transcend project sits. The Transcend project really sits in moving from the fundamentals of structure and microstructure into what's happening in terms of degradation. And the Transcend project is very much complemented by other projects. For example, we have the project supported in the UK by the EPFL. Nick is working on this project, for example, which is also concerned with water movement, so very, very close link here. We have the Synergia project between EMPA, EPFL, Dijon, and Paul Scherrer Institute looking at CSH. Later on today, I'm going to talk very much about CSH. And we have Core Project 9 and Core Project 8. So you see there's an interlinking of all these projects. So that's really the first part. And anybody got any questions on that first part? Is that all clear? Silence. Okay, so we'll go on to the second part, where in about 20 minutes or so, I'm going to try and tell you the basics of what concrete is. So what is concrete? Well, these are the ingredients that make up our concrete. You see, we start with cement, of course, and we mix the cement with water, and this gives us what we call cement paste, which is basically the glue. And this glue glues together the aggregates, which we can think of as kind of the skeleton of the concrete. And here, as I will explain, we have different sizes of aggregate. It's very important, this aspect of having different sizes. We go from sand, which is the fine aggregate, through to bigger and bigger rocks, which can be either gravel or crushed rocks. It says here additives optional. We're not going to talk much about this today, but additives are becoming an increasingly important part of modern day concrete. If we look at that and look at the life cycle of concrete, we take those raw ingredients, we mix them together, and then for between 3 hours or so, we have a workable fluid, and then we have this transformation from something that moves, where everything can move in space, to something that sets, becomes rigid. This is not a single point in time, but it's a continuous process, and that hardening process goes on over roughly the first 28 days or so. 28 days is a pretty arbitrary figure. It's just 4 weeks, so it makes it easy in terms of testing. But at 28 days, you will have about 80% of the ultimate strength of a concrete. And then over the next decades, or even centuries in some cases, you will have the service life and the durability. At the end of the life, as I said, you can actually break the concrete up. You can come back to these aggregates here. You can even put the other material back into the cement kiln, and you can recycle everything, depending on the economics and the logistics of the process. Now, what's really important to understand is we've basically got 2 levels of microstructure. We first of all got the level you can see with the naked eye. If you have a polished section of concrete, you can see the aggregates, the stones, and between the stones, you've got the cement paste, which is the grey bits, okay? So basically, in a typical concrete, you'll have about 60 to 70% by volume of aggregates, and the rest is cement paste. And your concrete should be designed that you have enough cement paste to fill up all the spaces between the aggregate, because clearly if you don't have enough concrete cement paste to fill up those spaces, then you end up with great holes in the structure, and that's clearly not a good thing. Then if we imagine to zoom in on this cement paste part of it, so this is our little magnifying glass here, and we zoom up about 2 orders of magnitude, so we're magnifying everything 100 times or so, we see something which would look basically the same, okay? Because it's all about packing particles and filling up volume. So at this second level of microstructure, this is the micron level, these are now cement grains, and at the start, these cement grains, the gaps between them, are filled up with water. And that's very important because the whole property we have of concrete, that it's fluid and we can put it into all different shapes, depends on the fact that we have enough water here to keep those cement grains apart and allow them to move relative to each other. So we're going to look first at this cement paste level. So if we look at this cement paste level, we need to think about this process at the beginning where the cement grains have to be able to move in the water. Now, if we take a very simple example of monosized grains, if you make a sort of close packing arrangement like this, a close packing arrangement of spheres, you can show geometrically that the maximum volume of solid you have can go up to 74%. That's absolutely the maximum for a close packed structure. Now, if we had something close packed like that, that's completely solid. You can't move anything in a structure that's that close packed. So in order to move things about, you have to space the grains apart a bit. And what you find is you have to space the grains apart till you come down to a solid volume fraction of about 50 to 60%. And what I'm trying to show in this graph here, this graph would apply to cement, but it would also apply to flour and water used for making cakes. It would also apply to any material that needs to flow. Is you see that as the solid volume, the amount of solid volume increases along here, the viscosity, that's the difficulty of moving the material, increases until you reach a kind of limit here. If you try to go beyond this limit, nothing moves, it's all blocked. Now, we can go a bit further, because if we have all grains the same size, that isn't actually very efficient. It's much more efficient to have grains of different sizes. Because if we have large grains like this, and then smaller ones and smaller ones and smaller ones, the smaller ones can fill in the spaces between the larger ones. And this is a way we can go up to higher volumes of solid packing. Okay? And in fact, I mean, this has been known for a long time. This is the principle of the famous Roman roads, which, as you know, have existed even up to nowadays, that they have this gradation of particles and the idea that the small particles fill the gaps between the large ones. And then finally, we have to put enough water in to fill the spaces between the cement grains. Now, okay, so what I've just told you there, is generally, in order to have something fluid, we can go up to about 50%, well, we need at least 50% volume of the liquid. And in reality, everything's about volumes. So, but in concrete, we can't, it's not really practical to measure volumes. If somebody says to you, right, I want 10 centimeter cubes of cement powder, how on earth are you going to work that out? Because you don't know in a cement powder how much is solid and how much is air. So it's almost impossible to work out. So it's much more practical to deal in weight proportions. And then in terms of concrete, basic concrete, we talk about water to cement ratios. So a typical water to cement ratio for concrete is 0.5. What does that mean? That means for every 1 gram of cement, we have half a gram of water. Right? Now we're just going to take 2 minutes on this exercise. It should be quite easy for you. But I just want you to try and do a very quick calculation that if the water-cement ratio is 0.5 and the density of cement is 3 grams per centimeter cubed, the density of water is 1 gram per centimeter cubed, try and calculate very quickly what the volume of solid is in that total assemblage of concrete plus water. Okay? So you've got 2 minutes to work that out. And it doesn't have to be very accurate. We just want a rough idea. So, anybody got an answer yet? What answer did you get?
No,
So a lot of people are looking very mystified. Has everybody got the idea how to do the calculation? Who's got an answer? One person. Sorry? Yeah, that's a good answer. So for those of you who are a bit lost, what you have to do, you have to say, okay, we've got 1 gram of cement, divide that by the density, gives me 0.33 centimeters cubed. And with every gram of cement, we've got 0.5 grams of water. And the volume of that is 0.5 centimeter cubed. So the total volume we have is 0.83. And therefore, the percent of solid in terms of volume is 0.33 divided 0.83, which is around 40%. Okay? So what's important, having done that calculation, is to see that here this 40% is right in the region we expected from this discussion of how much water we need to move everything around. If we've got about 60% water, 40% solid, this should be a nice, easy suspension to move around. Okay? Now, the second point, which is equally important and really concerns what happens at the end, is what it says down at the bottom here. What I'm telling you is that this cement, then when it reacts with water, it just about doubles in volume. So if I start with 40%, what do I end up with? Come on, that's easy. 2 times 40% is what? 80%. So what that says is that, very roughly speaking, for a typical concrete, I have about 80% solid, and I have about 20% of the volume, which is pores. And a volume of porosity up to about 20% is typical for a material that will give you a good mechanical performance. But this is basically what it's all about. It's all about filling up space and reducing the amount of pores. So if we now look here at a range of different cement pastes with different water-cement ratios, and this is typically the range you'll find used in the field. If you have a kind of standard concrete, you're not particularly worried about having something very, very strong, then you would use a water-cement ratio of about 0.6. And at the other end of the scale, if you want a very high-strength material, then you'll use admixtures to enable you to go down to this very low water-cement ratio of about 0.3. And here I've shown the equivalent volumes. And if you, just in your head, double those volumes, you can see that at this end, we get to a point where we can almost fill up all the space. So we can almost have no porosity at all. Whereas at this side, we're inevitably going to end up with a lot of space left over, which is going to lower the quality of the concrete. Now, the other way you can think about it is that the amount of water is really controlling the spacing between the grains. And that's what I've tried to show in these diagrams here, that as we go to higher water-cement ratios, the cement grains become more widely spaced. This makes it easier for them to move at the beginning, easier to place the concrete, but it then means you've got more space that needs to be bridged by this new product that's going to form during the reaction, this hydration. So now we're going to just see some very basic diagrams of this hydration, because this is the whole process that's going on that transforms our fluid concrete that we can put in place into a solid, that we get this grey material, the cement grains, reacting with the water to form a new product. That's the red stuff here, which is the hydrates. Okay? So that's a very, very, very basic scheme of what's happening that we're going to talk about in more detail later on today. And here, again, very diagrammatically, is that information shown in terms of mechanical performance, in terms of strength, that as the water-cement ratio goes up, we come to concrete of lower and lower strength. 10 megapascals would be quite enough, say, for example, for filling in a hole in the road. You could drive a car over it, no problem at all. But it maybe wouldn't be very durable because there's a lot of porosity that can then degrade over time. Now, just to finish, in the last 5 minutes, we want to go back to the other level of microstructure. So we've talked about the cement paste. This is the part that's really the business end of things, where things are happening, where we've got this chemical reaction going on, where we've got space being filled in, providing the glue for the concrete. But we need to think just briefly about this concrete end of things. And again, it's all to do with volumes. Now, we've seen in some detail what's happening in cement paste. And you see that in cement paste, we basically have about 50% of solid volume, and the rest is water. When we go into concrete, now the granular material is occupying a larger volume. And the reason we can have a larger volume of aggregates than we can of cement grains is because we have a larger difference in the size between the small aggregate and the large aggregate. There we can go over 2 or 3 orders of magnitude in size. And as I showed you before, because we have these very different sizes, this means we can increase the solid fraction. And to do that, the technology has been well developed. Okay, so this shows you what happens when you extract something like gravel. You sort it into piles of different sizes. You then, at the concrete batching plant, you have all these different sizes of aggregates. And you have a basic knowledge which has been built up by experiment, which tells you that if your aggregates have a grading which is in this kind of orange zone, this is a good zone for compact and workable mixtures. Okay, so we can see here that this size of the aggregates is on a log scale. So you see in this example here, we're going over 3 orders of magnitude from aggregate size well below 1 millimeter up to about 80 millimeters or so. Typically, maybe for common concrete like it's used for building these walls, the cutoff point would be about 32 millimeters. And on the basis of experience, we know that we want to have material in this region, and there are very simple ways we can reconstitute all our different fractions of aggregates to give us a total grading in this range. And those blue lines, these are just various curve-fitting exercises that people have made to give a kind of mathematical description of that orange zone. But it's important to realize that orange zone is really just the basis of a long knowledge and experiments over the years of what gives the best mixture. So we want to have that good gradation of aggregates, because if we have that good gradation of aggregates, the optimal aggregate packing, we can minimize the amount of paste, and that if we minimize the amount of paste, we optimize a lot of other properties. The paste, when it reacts, as we're going to see later, emits a lot of heat. That can give you a problem in large masses, so we want to reduce the self-heating. It's the paste phase that shrinks, so again we can reduce the shrinkage, and it's also the paste phase which contains the porosity, which is where the water and other ions come in that can lead to degradation. So for all these reasons, you want to have an optimal aggregate packing to reduce the amount of paste. And here's just some basic results from a colleague, Mike Thomas, in Canada. And you see this is the total water content in my concrete. And you can see how you put more and more water in. This is increasing the final permeability, permeability being the ability of water to move through the structure, or the amount of resistance. So this is a test which tests the electrical resistance, which is a measure of how easy it is for ions to move around. And you see both of these things scale with the total amount of water. The total amount of water is a combination of the water-cement ratio of the paste, but then the amount of the paste, which is brought about by this aggregate grading. So you see in these two examples here, the ratio of water to cement in the paste fraction was actually constant. And it's just the amount of cement paste that has been changed by having a better aggregate grading. So that's basically the end of this first part. What I really hope you've really managed to appreciate that it's all about volumes, that we're limited in the amount of solid we can put in at the beginning by the fact that it needs to be a fluid suspension, that what happens in this hydration reaction that we're go into in more detail is that we combine water in the solids to increase the solid volume, and that the key things, the two key things to do with concrete technology are really just about controlling the water-cement ratio and optimizing the aggregate grading. So I think we'll just have a 2-minute break there, but first of all, does anybody have any questions on that first part? Yes. Yeah, please do.
Hello? Yeah.
Yeah.
Just a small one about this curve to the aggregate grading. In
Yeah.
the past, I guess I heard something about that. It's named the Fuller curve. Is that right?
Yeah, it is the Fuller curve. Yeah, it's called the Fuller curve or the Bolomé curve, depending which country you come from. Yes.
Okay, thank you.
That was all the question was?
Yes.
Okay, yeah. It basically, there were a lot of different people who worked on that basic technology in the first sort of 20, 30 years of the 20th century. And, according to who did the experiments, they give their name to the curve. But they're basically all the same curve at the end of the day. Any other?